Welcome to an exploration of fluidic computing, where droplets become bits and flows replace circuits. Imagine a computer made entirely of fluids, where tiny droplets flow through microscopic channels to perform calculations, just like electrons flow through silicon chips. This is a microfluidic chip where droplets travel through channels thinner than a human hair, creating a new paradigm for computation. Let's start by understanding what microfluidic chips actually are and how they work. Microfluidic chips are devices that manipulate incredibly tiny amounts of fluids through microscopic channels, typically ranging from 10 to 500 micrometers in diameter. Channel widths are typically between 10 and 500 micrometers, about 1/10 the width of a human hair. To give you perspective, a typical microfluidic channel is about the same width as a human hair, but the droplets inside are even smaller. These droplets can be controlled with extreme precision, moved, merged, split, and routed through complex pathways. At these tiny scales, physics works differently than in our everyday world, and the Reynolds number tells us why. The Reynolds number is rho VL over mu, where rho is fluid density, V is velocity, L is characteristic length, and mu is viscosity. The Reynolds number describes the ratio of inertial forces, which want to keep things moving, to viscous forces, which create drag and resistance. When Reynolds number is much less than 1, viscous forces dominate, and flows are smooth and predictable. When much greater than 1, inertial forces dominate, and turbulence emerges. Let's calculate the Reynolds number for a typical microfluidic droplet to see what regime we're working in. Let's say our characteristic length is 100 micrometers, or 10 to the negative 4 meters. A typical droplet velocity might be 1 millimeter per second, or 10 to the negative 3 meters per second. Water density is about 1,000 kilograms per cubic meter. Water viscosity is about 10 to the negative 3 Pascal seconds. Plugging in our values, Reynolds number equals 1,000 times 10 to the negative 3 times 10 to the negative 4 divided by 10 to the negative 3, which gives us 0.1. With a Reynolds number of 0.1, much less than 1, the flow is completely laminar and predictable, which is perfect for computation. Now here's where it gets exciting. We can use these droplets as digital bits to represent information. The presence of a droplet represents binary 1, while the absence of a droplet represents binary 0, just like voltage levels in electronic computers. The key question is, can we build logic gates like AND, OR, and NOT, using only fluids and channels? The answer is yes, and the mechanisms are both elegant and surprising. Let's design a fluidic AND gate, one of the fundamental building blocks of computation. In a fluidic AND gate, two input channels A and B merge at a junction. The output only produces a droplet when both inputs have droplets simultaneously. Let's verify this works by checking the AND gate truth table. When A equals 0 and B equals 0, meaning no droplets in either channel, output equals 0. When A equals 0 and B equals 1, only one droplet enters the junction, which is not sufficient, so output equals 0. Similarly, when A equals 1 and B equals 0, we only have one droplet, so output equals 0. Only when both A equals 1 and B equals 1 do we have two droplets that merge to create an output droplet. Output equals 1. To understand how droplets behave at junctions, we need another dimensionless number called the capillary number. The capillary number is mu v over sigma, where mu is viscosity, v is velocity, and sigma is surface tension. The capillary number compares viscous forces that deform droplets to surface tension forces that keep droplets spherical. For a water droplet in oil, surface tension is approximately 0.05 newtons per meter. Using our previous values, capillary number equals 10 to the negative 3 times 10 to the negative 3 divided by 0.05, which gives 2 times 10 to the negative 5. With capillary number much less than 1, surface tension dominates and droplets maintain their spherical shape, which is crucial for predictable behavior. For computation to work, we need to control the timing of droplet arrival with precision. Volumetric flow rate Q equals velocity V times cross-sectional area A. For a 100 micrometer diameter channel, radius is 50 micrometers, and area equals pi r squared, approximately 7.85 times 10 to the negative 9 square meters. At 1 millimeter per second velocity, flow rate Q equals approximately 7.85 times 10 to the negative 12 cubic meters per second. Converting units, this is about 7.85 picoliters per second, an incredibly tiny amount. Let's calculate how long it takes for a droplet to travel 1 centimeter through a channel. Time equals length over velocity, which is 0.01 meters divided by 10 to the negative 3 meters per second, giving us 10 seconds. This 10-second transit time effectively sets our clock speed, meaning fluidic computers operate much slower than electronic ones. How does fluidic computing speed compare to traditional electronic computing? Fluidic gates operate at about 0.1 Hz, processing one operation every 10 seconds, while modern electronic processors run at 3 GHz, billions of operations per second. The speed difference is 3 GHz divided by 0.1 Hz, which equals 30 billion times faster for electronics. You might wonder, if fluidic computing is 30 billion times slower, why would anyone pursue it? Fluidic computing has several unique advantages that electronic systems cannot match. Fluidic computers can directly manipulate chemical and biological samples, performing computation and chemistry simultaneously. They produce no electronic interference, making them ideal for use in explosive environments or near-sensitive equipment. Thousands of droplets can be processed in parallel across a single chip, compensating for slower individual operation speed. Here's a representation of parallel processing, where many droplets are manipulated simultaneously across different channels on the same chip. Let's analyze the energy requirements for moving droplets through microfluidic systems. Power P equals flow rate Q times pressure drop delta P. For laminar flow through a rectangular microchannel, we can use the Hagen-Poiseuille equation. Pressure drop equals 8 mu LQ over pi r to the 4th power, where L is channel length and r is radius. Substituting our values for a 1 centimeter channel, we get 8 times 10 to the negative 3 times 0.01 times 7.85 times 10 to the negative 12, divided by pi times 50 micrometers to the 4th power. This gives us a pressure drop of approximately 32 pascals, which is quite small. Power equals 7.85 times 10 to the negative 12 times 32, which is approximately 2.5 times 10 to the negative 10 watts. That's only 0.25 nanowatts per channel, making fluidic computing extremely energy efficient compared to electronic transistors. Can we build more complex circuits? Let's design a full adder using fluidic logic gates. A full adder is a fundamental circuit that adds 2 input bits A and B, plus a carry-in bit, producing a sum bit and a carry-out bit. The inputs are A, B, and C in for carry-in. The outputs are S for sum, and C out for carryout. A full adder requires XOR gates, AND gates, and OR gates connected in a specific network to perform addition correctly. Implementing a full adder in fluidic logic requires approximately 20 to 30 individual droplet junctions and merge points. What are the real-world applications of fluidic computing systems today? Lab-on-a-chip devices use fluidic logic to perform medical diagnostics, analyzing blood samples, and detecting diseases automatically. DNA sequencing platforms use microfluidic manipulation to sort and analyze genetic material with minimal sample volumes. Pharmaceutical companies use fluidic systems to test thousands of drug candidates in parallel, dramatically accelerating discovery. A typical lab-on-a-chip takes samples in on the left, processes them through fluidic logic circuits, and outputs results on the right, all on a chip the size of a credit card. What are the fundamental physical limits and engineering challenges for fluidic computing? There's a minimum droplet size, below which surface tension forces make droplets unstable and difficult to control precisely. Minimum radius is roughly sigma over delta P, about 0.05 divided by 1,000 pascals, giving approximately 50 micrometers. At microscales, evaporation becomes a significant problem, potentially changing droplet sizes during computation. Manufacturing imperfections in channel geometry can cause unpredictable droplet behavior, limiting computational reliability. The most promising future might be hybrid systems combining fluidic and electronic computing. Hybrid systems use electronic circuits for high-speed control and decision-making, while fluidic systems handle physical manipulation of samples and reagents. Electronic components provide fast control signals to valves and pumps that manipulate fluid flow. Meanwhile, the fluidic components directly interact with chemical and biological samples, performing the actual experiments. How does information density compare between fluidic and electronic systems? Modern transistors are about 5 nanometers, or 5 times 10 to the negative 9 meters. Microfluidic droplets are about 100 micrometers, or 10 to the negative 4 meters. The area ratio is 10 to the negative 4 squared, divided by 5 times 10 to the negative 9 squared, which equals 400 million. Electronic transistors are roughly 400 million times more area efficient for storing and processing information. However, fluidic bits can carry chemical information, like the identity and concentration of molecules, which electronic bits cannot. Looking ahead, could fluidic computing evolve into programmable matter? Imagine a material where channels can be dynamically reconfigured, allowing the same physical substrate to perform different computations based on how flows are routed. Future systems might feature self-assembling fluidic circuits where droplets organize themselves into computational networks. These systems could adapt their processing based on the chemical composition of inputs, creating truly intelligent materials. Let's reflect on what fluidic computing teaches us about computation. Fluidic computing demonstrates that computation is fundamentally substrate independent. Any system that can implement logic gates can compute. The laws of physics set ultimate limits on what's possible, but human creativity finds unexpected paths within those constraints. There's a fundamental trade-off. Speed times power times versatility tends to be roughly constant across computing paradigms. Electronic, fluidic, and quantum computing represent different points in the space of possible computational substrates, each with unique strengths. Fluidic computing will likely never replace silicon for general-purpose computing due to fundamental speed limitations. However, it opens entirely new possibilities in applications where chemistry and biology meet computation, creating capabilities that silicon alone cannot achieve. Let's summarize the key insights about fluidic computing. First, microscopic droplets flowing through channels can represent digital information, with presence or absence encoding binary states. Second, low Reynolds numbers at microscales create predictable laminar flow that's ideal for implementing logical operations. Third, fluidic computers operate millions of times slower than electronic processors due to physical fluid velocities. Fourth, their unique advantage is direct manipulation of chemical and biological samples during computation. Fifth, hybrid systems that combine electronic control with fluidic manipulation offer the best of both worlds. And finally, practical applications in medical diagnostics and pharmaceutical research are already deployed and saving lives today.